Uh, Good morning. So let's get started to not delay all the other presentations. So I will make a very brief introduction. This idea of organizing a school and workshop on American monsoon took shape during my first term as a member of the CSIRO Monsoons panel. And the co-chairs of this panel were very supportive of this idea. And one of the tasks of the panel members was to organize regional working groups on monsoons. And once our working group was formed, I presented this idea to them, and they also were very enthusiastic about this idea. So finally, after many months of hard work, we can say welcome. More than 1 year, yeah. Welcome to all of you to this workshop and advanced school on American monsoons. The organizers are myself from the University of Paraná, Federal University of Paraná, Iracema Cavalcanti, whom most of you know, but stand up, Iracema, and Manoel, both from the National Institute of Space Research in São José dos Campos, here from São Paulo. So we are very happy to welcome you here in this event. Well, this is the membership of the American Monsoon Working Group, and I'm very glad to say that all of them will be here. They are not all of them here yet, but all of them will be here and will contribute with talks to this workshop. Well, I think I will skip this about the objectives of this working group. You can see it in the internet page of CSIRO. And what's important is to acknowledge the support we received to make this event reality. So we received support from International Center for Theoretic Physics in the ICTP in Trieste, from CSIRO, Climate and Ocean Variability, Predictability and Change, GEOX, Global Energy and Water Exchanges, which are core projects of the World Climate Research Program. We received also support from the International Union of Geodesy and Geophysics, from FAPESP, Fundação de Amparo à Pesquisa do Estado de São Paulo, and all the local organization was provided by the ICTP South American Institute for Fundamental Research, which by now all of you know, because it was in their internet page that all the information about the workshop was displayed. And well, this institute is in the Theoretical Physics Institute of the UNESP, which is a university of the state of São Paulo. I want especially to thank all the people from this South American Institute for Fundamental Research for their local organization. They were always very supportive, very efficient in organizing it locally, in providing people who got support with information. So we are very grateful to them. And, well, now a brief talk, 5 minutes, answering this question, because many people do not know that there are American monsoons. They know about Asian monsoon, especially Indian monsoon, but public in general are not very aware that there are American monsoons. Actually, the fundamental monsoon characteristics, such as basic definition, what is a monsoon system, and geographic range has undergone some changes in the last decades. So the modern definition of monsoon climate is based on both the annual reversal of surface winds, which is the classical definition, basis of the classical definition, and the contrast between rainy summer and dry winter season. Whereas in the classical definition, it was based mainly on the annual reversal of surface winds. So when we look at the classical criteria for a monsoon, as specified by Ramage, for instance, in this work of 1971, we see these conditions here. So prevailing winds wind shifts 120 degrees between January and July, between these two, the winter and summer. The average frequency of prevailing wind is more than 40%. Speed of mean wind exceeds 3 meters per second. And there is a criterion regarding the pressure, the steadiness of pressure patterns. So if these criteria, these classical criteria are applied, these are the monsoon regions. So you can see that there are only monsoons in the eastern hemisphere. And that's why the American monsoon are not so well known. But then, more recently, several authors proposed other criteria. And I will present here the criteria specified by Wang and Ding in 2008. So, according to them, summer minus winter precipitation difference must exceed 300 millimeters. And the summer precipitation threshold must exceed 55% of the annual total. So summer here is not just 3 months. It's May through September for the northern hemisphere and November through March for the southern hemisphere. And then applying, well, these criteria, as you can see, are based on precipitation, but they are dynamically linked to some criteria, here you can see it, to some criteria related with low-level zonal winds. When these criteria are applied, then the tropical monsoon wind zonal wind at 850 hectopascal show reversal. They are westerlies in the summer and easterly in the winter, with summer minus winter exceeding 50% of the annual mean. Of course, the domain of this wind criteria here, which is delineated in black here and here, they are, this domain related to these wind conditions these domains are not in the same place as the domain related to these precipitation criteria, but they are dynamically linked. So here in green, you can see the regions of monsoon precipitation, and now you see that there is a monsoon regime here over the Americas. And here in the Eastern Hemisphere, these criteria, they are very consistent with the region delineated by the Ramage criteria. Actually, they are very coherent. But using or adding these criteria related to precipitation, so this American monsoon here, and also this Southern Africa monsoon is included as monsoon regions. So in South America, this results in this monsoon region here, using this criteria. So you can see that it covers almost all the continent, the most populated regions, the regions where agriculture is very important, generation of hydroelectric energy is very important. So the monsoons actually are the support of livelihood of millions of people, are very important to economic sector that are crucial for South America as hydroelectric generation, agriculture, and therefore we are fully justified to have this monsoon workshop. Here you can see what I just mentioned, that here you have Southern Hemisphere winter, and you can see that the prevailing direction of the zonal wind here in that region that was delineated in black in the other figure are easterlies, the zonal components. Whereas here, during the summer, they are westerly. So there is a reversal of the zonal wind, not of the wind itself, but the zonal component reverses. Well, so as I said, the modern definition is based on both the annual reversal of surface wind and the contrast between rainy summer and dry winter season. Whereas the classical definition is based on winds, on the reversal of surface winds, and confines monsoons to the Eastern Hemisphere. And even includes some mid-latitude areas which exhibit winter precipitation maximum and belong to Mediterranean climate regimes, in contrast to the modern definition. And one of the motivations for this modern definition is the considerable socio-economic scientific importance of monsoon rainfall in these regions that were by this modern definition. And well, so there are American monsoons. How strong are they? Here you have a figure from this review paper on American monsoon by Ver et al., 2006, which shows the annual cycle of precipitation in chosen core monsoon regions in all these monsoon domains around the world. And you can see that here you have South America, this blue line. You can see that the contrast between summer precipitation and winter precipitation for South America is even stronger than the contrast between summer precipitation and winter precipitation in India. So it's a very intense monsoon system. So we are justified to having this workshop and enjoy the workshop and the school on American monsoon. Thank you. So I am very glad to announce the first lecture, the first invited talk, which will be delivered by Wenju Cai, who is the chair of the scientific steering group of CLIVER, which was one of the main supporters of this workshop. Wenju Cai is a great scientist. His agenda is always full, but he reserved 2 days for our workshop here in Brazil. Thank you very much, Wenju.
Talk here, right?
You want the microphone?
Okay. And this one too. Very good.
No,
Do you need both? Can you?
You can use this and then this pointer. Perhaps then you have a hand free for the pointer. Unless you, no, if you want to use this, you don't need this.
Okay, but I saw you use both.
Oh, really? I didn't notice.
Yeah, you could.
I guess so.
Why not? That's right, yeah.
What's yours?
Yeah, that's the one.
ENSO.
This is the one,
ENSO,
yeah.
Under greenhouse one.
So that's the pointer. That's the what's the next slide? Okay, it is actually a pleasure to come to Brazil. This is my first visit to Brazil, and I expect that I will come more often because it's such a nice experience. Seeing such a big city and everything seems to work in an orderly manner is such an amazing experience. But firstly, I'd like to thank Alice for inviting me here. And on behalf of CLIVER Scientific Steering Committee, I'd like to thank Alice for spearheading this workshop. Now, I'm in there and I'm watching Alice working really hard for this workshop. And it is such pleasing to see that you had a great champion in South America for the young students to study the monsoon. That definitely you don't need justification, although I thought you provide very nice scientific justification. And I also like to thank the local organizing committee. Everything seemed to be so smoothly running well and nicely organized. Because it's my first to Brazil, I was a little bit, not nervous, but a bit see how can I go in there? Because I arrived last night, and this morning, magically I arrived here with so many people here. So it is really wonderful. So coming here to support is actually my main goal. This is not important because this is ENSO. This is not monsoon. But nevertheless, I'm already here. I may as well talk a little bit about some of the work that we have done on ENSO's response to global warming. And if I look at the modern definition of Alice's modern definition of monsoon, it seems that ENSO affects the monsoon. Yeah, so it's really a main driver or a main player of the monsoon system, if not a driver. So today my talk is an old talk, So I wanted to come here and learn with you about ENSO's impact, how ENSO responds to climate change. And to start with, I'd like to acknowledge many of my colleagues. It's not a complete list in this body of work. So we all know what is El Nino. So normally in the tropical Pacific, you had the trade wind that blow from the east to west, pushing the warm water to the western Pacific. And that drives this deep convection, heavy rainfall, ascending motion. And at high in the hemisphere, you got a sinking motion, sending the dry and cold air to the eastern equatorial Pacific. And so basically here, normally in this part, in Ecuador, Peru is normally quite dry because of the substance there. But this trade wind also drive an upwelling, a shallow thermocline. So you got this thermocline sloping this way, and this cooling, this upwelling drive the cooling, which in turn support this easterly trade wind. So there is a positive feedback in the seasonal scale. Now, during El Nino, so every 2 to 6 years, what you have is the trade wind relaxes, weakens. So this convection shift from the western Pacific to the central and eastern Pacific. So you now get rainfall in this region, but in the western Pacific, you got the drying, anomalous drying condition. Now here, you have the Ecuador normally. In a traditional El Nino, you start to have heavy rain and so on. And again, this is a sort of Biochemical feedback in the opposite direction. So you had the trade wind relax, which in turn drives a weakened upwelling and deepened thermocline in turn reinforcing the warming. So the zonal gradient weakens further, and you got this positive feedback. That is what we call normally a traditional view of an El Nino. Now during La Nina is actually the reverse. But you can also view it as the intensification of the seasonal cycle. So this trade wind is stronger, upwelling is more intense, thermocline is more slope here, and this deep convection in the western Pacific is now more intense and concentrated in the maritime continent. So the Americas tend to have dry condition and so on. So this is what we think ENSO, right? El Nino and La Nina. So during the huge El Nino 1998, 1997, in Peru, you have the marine life died en masse because the food they prey on, anchovy, is no longer there, and you have the flood in Peru and Ecuadorian region. So in Australia, where I come from this trip, come from Sydney, Melbourne, and then Melbourne to Santiago to Sao Paulo. So quite a long trip yesterday. And so in Melbourne, we tend to have bushfire in 1982-83. That is in February, Ash Wednesday. On that day, I just arrived a year later, or a year a bit later, I arrived in Australia, and my supervisor's house was burned a couple of years ago, and he was in the process of building. But El Nino tend to have a huge drought in Australia, and also dust storm in Melbourne, February. But in the South Pacific, we had the ITCZ, Intertropical Convergence Zone and South American Convergence Zone. So during El Nino, normally for example, this ITCZ shift towards equator, and the SPCZ also moves towards equator. Now La Nina is actually the reverse, move away from the equator, and so on. So now La Nina also has its impact. For example, 1998 in China, killing thousands of people and more than 200 million, equivalent to the whole of Brazil, was affected in China in 1998, the biggest flooding of the century. And of course, we also in Australia, in Brisbane, we also had the huge flood. Now, after the 2015-16 El Nino in Wuhan, in China, also had a flood. So this 1998 is the strongest La Nina of the 20th century. So it often occur after an extreme El Nino because an El Nino would shallow the thermocline, allowing the subsurface ocean to be more coupled with surface ocean in the central equatorial Pacific. So El Nino really affects many, many things. It affects Indian Ocean dipole, affects the Atlantic variability, Indonesian through-flow IPO, interact with MJO and tropical cyclones. So really, it's really quite important in terms of the global climate variability and impact. So often, and you all know this, but often we use, in oceanography, we use indexes like Nino 3 index, and sea surface temperature index to describe El Nino. And nowadays, we use it to describe so-called Eastern Pacific El Nino. Now, Nino 4 in the Central Equatorial Pacific, Central Pacific El Nino, and Nino 3.4 is a mixture of the two. So you could actually capture almost all events. So how El Nino, how ENSO will respond to climate change has challenged scientists for many, many years. Ever since the 82, 83 El Nino, we'd like to know how it will respond to climate change. But many years ago, I was the CLIVA Pacific Panel Chair, and we organized this paper, and I asked Matt Collin to lead that paper. So what we see is that if we look at the standard deviation of Nino 3 changes in the present day and in the future. So basically, there is no intermodal consensus on how it will respond. So then I was invited to write this paper in 2015. So what we really could say, again, there's not much. It's the same thing. There's not much intermodal consensus in terms of how Nino 3 standard deviation will respond. So here is the pre-industrial from some 30 models or so. 20th century in terms of standard deviation, RCP 4.5 or 8.5. There's no intermodal consensus. You can see there is no discernible changes from these scenarios using Nino 3 index. However, most of the model produce some consensus. And these consensus could be summarized in the 4 areas. Firstly, there's a weakening water circulation with a faster warming in the equatorial eastern Pacific. There's increasing vertical temperature gradient. Thermocline shallows from the black line in the present day to the future in red. And there's a faster warming in the maritime continent than the ocean next to it. And there's faster warming in the equatorial region, if you average the equatorial region, than the off-equatorial region. And for example, this kind of warming pattern is important for the convergency zone, because convergency try to follow where the maximum temperature is. So almost each of these mean climate changes has an implication for ENSO's change. So in terms of rainfall variability, for example, if we look at the SPCZ, so in 82 and 83, extreme El Nino, 97, 98, or in a not so strong El Nino, in those 3 years, these SPCZ shift towards equator by 1,000 kilometers from the normally 200 kilometers, and causing huge impact to the South Pacific island countries, drought and flood. More importantly, it also takes the tropical cyclone genesis, which is maximum around 500 kilometers south of the convergency zone, towards regions where they don't normally expect tropical cyclones. And so you have huge impact from this kind of what we call zonal SPCZ events. So one of the implications for this faster warming along the equatorial region than the off-equatorial region is that even if SST variability does not change, this kind of extreme swing will occur more often. And this was published in paper in 2012. So extreme swing of the convergence zone can occur more often under greenhouse warming. If we now look at extreme El Nino, so this is the extreme El Nino composite, 82, 83, 1997, 98, in terms of our summer, December, January, February, rainfall and SST. So these are the SST, total SST. So that is the 28 degrees C isotherms. You can see during the extreme El Nino event, it spread across the Pacific. And if you look at the heavy rainfall contour, the 5 millimeter per day average on that season, it also spread across to the Pacific and covers the eastern equatorial Pacific region. So you can actually try to construct a meridional temperature gradient, the off-equatorial minus the equatorial region, and that gradient for those two events are actually negatives, meaning that the ITCZ has now shifted towards the equatorial region during those extreme El Nino events. No wonder the rainfall is so huge. So a deviation from the conventional El Nino definition is for extreme El Nino, not only the convergence zone shift from Western Pacific to the Eastern Equatorial Pacific, the ITCZ also shift move towards the Eastern Equatorial Pacific. And so if you look at that meridional gradient of equatorial, take away from the equatorial, of equatorial minus equatorial, 1982, 83, 1997, really is negative. Maximum is on the equator. And rainfall increased dramatically. In this event, 10 times of the normal situation. So that caused a huge rainfall skewness. Now this is the 2015, 2016. So it's about over 5 millimeters per day in the Nino 3 region. So if we could define extreme El Nino as when the rainfall in DJF average is greater than 5 millimeter, then you could say, let's look at the present day climate and future climate in climate model, how these may change. And so we pick up 20 models in the IPCC's CIMET 5, and in this paper also CIMET 3, 20 models that are able to simulate this kind of nonlinear relationship. So each model has 200 years, 100 in the present day, and the other one in the future climate. So in this panel, we have 2,000 years of virtual climate and looking at that relationship. So the extreme is about 1 in 20 years, so 100 years per 2,000 years. Now in the future climate, that doubles. And this is despite there is no consensus on how Nino 3 SST may change. So there's a doubling in that kind of huge reorganization of atmospheric convection. So why? How? So this is a paper that we published. So in the present day climate, you may need 2 units of anomaly to move these convections. But in the future climate, because this is already warming faster, so it is easier, even if SST variability does not change, it's easier to have a huge maximum temperature anomaly in this region. So it doesn't take 2 units of the anomaly, only 1, less than 2, to generate this huge movement of convection. So easier to shift convection, to have the massive reorganization of the atmospheric circulation under global warming because of the mean state change. So that's implication for rainfall. So the Paris Agreement, Trump has withdrawn from Paris Agreement. So in this paper, one of my postdocs was trying to look at what happened under the Paris Agreement to the extreme El Nino events we define in this way. So, and what we find is that if you look at, there are not many models that runs under these scenarios, RCP 2.6, in order for us to get to that 1.5 to 2 degree warming relative to the pre-industrial level. So here is the from 5 models that goes to 2030s. So here's its global mean temperature in black color, and that's the range from the 5 model, the gray. So you can see that by 2050, the global mean temperature stabilize and start to decrease a little from 2050 level. But that meridional gradient, the reverse of meridional gradient, continue to weaken. This is negative sign, so continue to weaken for another 100 years. And the extreme El Nino continue to increase for another 100 years. That means the maximum risk is not at when the maximum warming occurs. It could occur 100 years later in terms of this huge rainfall increase as definition of the extreme El Nino. So the bottom line is under global warming rainfall, sensitivity to sea surface temperature variability increases even if sea surface temperature variability does not change because of the mean state has changed. Now in terms of sea surface temperature variability, that is what we really wanted to know. And if we now look at the weakening water circulation and faster warming, that also has implications for characteristics of El Nino. We know that during those extreme El Nino, 82, 83, and 97, 98, the sea surface temperature along the equator, this is along the equator and time going upwards. You can see that eastward propagation, which is extremely unusual because we know the trade wind and the oceanic current actually go from east to west. But this is actually going from west to east. So one of my postdoc, Agus, looked at the issue. He found that the region that you could do that, you can have an eastwards propagation, is because if you look at the upper oceanic current along the equator, this is a negative value going from, meaning it's going from east to west, right? Westwards. So during those events, actually the mean current, the current actually reverses. Because of that reversal, it allows the sea surface temperature to propagate from west to east. And we know that this mean current, because the water circulation is weakening, so that mean current is weaker. So even if variability does not change, you may have more chance of a reversal. So he then looked at the events of eastward events in 38 models, CIMIT 3 and CIMIT 8. And here we show the occurrences in blue in present day and future. You can see that in the future, the eastward propagating events increases in frequency. But many of the events occur without a big El Nino. So this issue of how extreme SST El Nino warm events may change has not been resolved after this paper. So the other one is increasing vertical gradient. This increasing vertical gradient, it also has implications because in the Central Pacific, the subsurface ocean normally is quite isolated from the surface. So when it shallows, it becomes the coupling between the subsurface and the surface ocean to strengthen. And this paper found out when that occurs, Central Pacific El Nino is able to occur more often. So this is a paper in 2009 looking at the relative frequency of Central Pacific El Nino and Eastern Pacific El Nino. So in the red is the present day, the blue is in the future. So majority of the models show an increased in the future of Central Pacific El Nino relative to the Eastern Pacific El Nino, because the Central Pacific in the Central Pacific, the upper and lower ocean is more strongly coupled under climate change. But if you look at these two together, the maritime continent, when maritime continent is warming faster, convection is easier to establish, to be more intensified. And that is when extreme La Nina occurs. So extreme La Nina really, if you compare the moderate La Nina and extreme La Nina also tend to have a center in the Central Pacific, but it extends further towards the maritime continent, and it's much cooler. So pushing the convergence zone to be more intense and concentrated in this region. And you can actually construct a zonal gradient between the maritime continent and Central Pacific to get a gradient. And here is the gradient. So you can use Nino 4 to describe the SST variability for La Nina. So when that gradient become more negative, you got this, you pick up these two largest extreme La Nina in the 20th century, 1988 and 1998. So we define extreme La Nina, go back. So we define extreme La Nina to be that when Nino 4 is greater in amplitude than 1.75 standard deviation. And you can look at this relationship in the future climate, properly retrain the time series of Nino 4. So in the present day climate, we've got 21 models. You got 92. In the future, you got 75% more. And this bracket number indicate the extreme La Nina that occur after extreme El Nino, because we know after extreme El Nino, the thermocline shallows. The Central Pacific thermocline is more closer to the surface. And basically most of the increase in the extreme La Nina events occur after an extreme El Nino. So basically about 80% of the increase, 159 minus 192 and 73 minus 24. So about 80% of the increase in extreme La Nina occur after an extreme El Nino in the future climate. And the reason is that after extreme El Nino, this is the 82, 83 difference and the all events. After extreme El Nino, the thermocline shallows in this part of the equatorial Pacific, allowing the cooling to be more easily generated. So, what happened to Nino 3? This is Nino 4 SST. So this really, it is an issue for many, many years, since 82, 83, 97, 98. So if we look at the standard deviation of Nino 3 in 34 CMIT-5 models, and in blue in the present day climate from 1900 to 2000, in future in red color, 2000 to 2100s. And the RCP 8.5 scenarios, 16 out of 34 models generate decreased variability in Nino 3 standard deviation. That means 18 produce an increase, half-half. So what does it mean by using Nino 3.4, using Nino 3 for all models? It really assumes that every model generates an anomaly center, the same as in the observation, right? The same as in the observation. So is that true? Also, it doesn't take into account of the ENSO diversity. Each model's diversity could be very different. So this was published in December last year, on the 8th of December. It was accepted in 18 days, the paper. It's one of my records. And so the idea is so simple. So we know now there are two kinds of El Nino, strong and moderate El Nino, right? So Ken Takahashi and many other people has shown that. So you got two centers of El Nino. For La Nina, if you compare the weak or moderate or strong, I mean the center tend to be in the Central Pacific. So you now have two types of El Nino, and the La Nina is not a mirror image of El Nino. So the answer is much more complex. It's diverse. There is asymmetry. That means you can't use Nino 3 or Nino 4 alone to represent ENSO. You need two indexes. So often we can use UF analysis to get two patterns of sea surface temperature. This is the first and second. Now the first really is strongly correlated with Nino 3.4. It's really the average of all El Nino events or La Nina events. And this second pattern modified to get the patterns from one year to another that is different. So if you look at this, the time series, UF1 and UF2, you can see these two time series are non-linearly correlated. And in fact, the Eastern Pacific El Nino is the difference between this and that, give you this pattern. So you can use an E index, Eastern Pacific El Nino index, Eastern Pacific ENSO index to describe Eastern Pacific. And the Central Pacific El Nino is the sum. If you have this pattern, add to that pattern, you get maximum warming in the Central Pacific. You get this pattern, right? And if you reverse it, but they are not symmetric. If you reverse this, it gives you the La Nina. So extreme La Nina will be the negative of those two patterns sum with some coefficient, UF1, UF2. Now you can see that La Nina tend to have bigger negative value than the Central Pacific El Nino. And so that this kind of treatment allow you to look at diversity, asymmetry between El Nino and La Nina. So if you look at all the analysis, and you can actually construct, describe this nonlinear relationship, or that one. So PC2 is actually a nonlinear function of PC1 with an alpha in front of it. Now, this nonlinear relationship really describe summarize the processes that give you this diversity, nonlinearities between ENSO and La Nina. So El Nino and La Nina. So let's remember this number is a negative number because it's the arc is towards south, negative value. So let's now look at the E index from observations from 1950 onwards. So E is the PC1 minus PC2 divided by square root of 2. So you can see there's a positive skewness. El Nino in the Central Pacific is able to grow much bigger than La Nina, than cold conditions in the Eastern Pacific. Eastern Pacific El Nino is able to grow much bigger than the cold anomalies. And in the Central Pacific, the C index, those La Ninas, those negatives are much bigger than the positives value. So there is a positive skewness for E index and negative skewness for C index. As we know, extreme La Nina is much bigger in the Central Pacific than the Central Pacific El Nino. So, so the center of positive skewness is actually the center of Eastern Pacific El Nino. The center of negative skewness is the center of CP-ENSO, right? By definition, this is just by definition, where the maximum of positive skewness will be the center of Eastern Pacific El Nino. So this kind of description is quite nice. And the reason for that, again, there's quite many papers, and including just one paper that just appeared in GIL by my student. The reason is that if you look at the relationship between wind and Central Pacific SST C index, and you get this slope when the temperature is positive, and the other slope when the temperature anomaly is negative. There is this 1.5 magnification, so it means that when the temperature is warm, the wind response is greater. But in the eastern equatorial Pacific, it's huge. This nonlinearity, so once convection is established, the wind's response to sea surface temperature increase nonlinearly. But in order to get this convection established, you need a gap. And so basically, that's why in this one you have this kind of nonlinearity, and there's a gap here. So this atmospheric response, nonlinear atmospheric response to SST in the eastern Pacific is really an important dynamical forcing of the ENSO diversity and nonlinearity. So we can do all this analysis that I just show you for observation to all the models in the world, 34 climate models. And you can get your E pattern, right? E pattern. Once you have the E index, you can construct your E pattern. Now this is an E pattern in one model. This is another E pattern, Eastern Pacific El Nino ENSO pattern, in another model. You see how different they are. You can no way represent this pattern by linear 3 and the same as this pattern also by linear 3. That means using linear 3 to examine how ENSO may respond to climate change is not the right approach. You should perhaps use E index. Because using E index implying that you are looking at how this pattern in this model, unique to this model, with the center here, will respond to climate change. And in this model, you are looking at how this pattern, with the center here, in closer to South America, will respond. And if you just use linear 3, you're missing the point. You're missing the anomaly center. And so that's exactly what we do. So you just use this E index, and you examine how in the present day climate in blue and in the future. So you do absolutely nothing. You just can using this E index. You now get 24 out of 34 models generating an increase in variability of the E index. So that's now 75 models showing an increase compared to almost half in a linear 3, which is a greater consensus. But we know that not all models could generate these nonlinearities. For example, if you look at correlation between linear 3 and linear 4 in the observation, is much weaker than many of the models. Now in this model, they can't tell linear 3 from linear 4. They can't tell Eastern Pacific from Central Pacific El Nino. And therefore, we need to select models. We need to select models. Now, in the observation, we got these 3 numbers: alpha, E index skewness, and C index skewness. Now, what are the relationship between the 3? You got one world in the observation, one realization of the real world. We don't know what are the relationship between these 3. But in models, we can see, so we calculate the alpha and the skewness in E for all these 34 models. You can see this: the bigger the alpha in amplitude, the greater the positive skewness. So alpha is a measure of the skewness. Now skewness has a nonlinear process going into it, which I talk about many due to nonlinear atmospheric response. But the bigger the alpha in amplitude is also the bigger the C skewness, negative skewness. Why? Because if you have a more extreme El Nino, that extreme El Nino will give you more extreme La Nina, and therefore you will get bigger negative skewness. So this is really nicely related, correlation of 9.92. So alpha really links the two things. Now observation, this is the observation, minus 3.1 and 0.31, but you can see many models are not producing that. Some models even produce a negative skewness or positive alpha. About half of the model can produce half of the observed. So we choose those half, 17 model, give you this nonlinear relationship. And so, as I said, the alpha is really a nice parameters. So in these 17 models, you got quite realistic sort of nonlinear relationship. But in the other 17 models, you get this. So we are going to just focus on those 17 models to see how ENSO, as depicted by E index and C index, may respond to climate change. So this is some of the good models. In 200, each model has 200 years in the good models. And they tell apart the Eastern Pacific El Nino and Central Pacific El Nino. These are some of the not so good models, right? So you can imagine with this kind of model, for any E index, it could be a multiple combination because there is not a sharp linear relationship in this quadrant, right? So these are the models that are not able to tell apart a Central Pacific from an Eastern Pacific. That means the nonlinear dynamics in this model are not well simulated. And so in this, in the selected model, you got this nonlinear relationship between the wind and the SST. So the magnification is 2.5. Now in the observation, about 3.5, right? So yeah, and that's so in the Central Pacific as in the observation. So if we now focus on that 17 models, 15 out of the 17 models produce an increased variability in E index. And most of them translate into an increase of extreme El Nino, defined as when the E index, this E index is a sea surface temperature index, greater than 1.5 standard deviation, about 50% increase in terms of sea surface temperature variability. And so a little bit on the mechanisms. So under climate change, stratification intensified, and so the thermocline shallows from the green to the red to the black. You can define a temperature gradient, average in this box minus at a depth, and you can see the relationship between the increase in the variability and this vertical gradient. So the greater the increase, this is 17 models, the greater the increase in the vertical stratification, the greater the increase in the E index. And this R square is 0.56. So under climate change, because the thermocline is shallowing, the stratification is intensifying, the same amount of wind is actually applying to a shallow, effectively shallowing depth. So the ocean atmospheric coupling is actually stronger. How about C index? Now the same dynamics apply to C because the intensified stratification also enhance the coupling for C. Now you have 10 out of 17 produce an increase in C index. 11 out of the 17 model produce an increased occurrences of CP El Nino greater than 1 standard deviation. Huge increase in La Nina, extreme La Nina. The C index and Nino 4 are the same. We use Nino 4 in a previous paper to define extreme La Nina, but C index could also give you this definition. So that is the story so far, but there are a lot of uncertainties. Models still suffer from the cold tongue bias. So there's a paper under review looking at the impact of cold tongue bias on what I just tell you. Basically, if you correct this bias, the increase will be bigger. It's a paper in Nature Climate Change. Hopefully will come out soon. Now we also had discussed about the interbasin interactions. Climate models are not able to simulate the correct inference from Atlantic to Pacific or Pacific to Atlantic, which is actually very important to studying ENSO's impact on South America's rainfall. One of the things that I'd like to show here is that if you look at models in blue color, there's a group of models which cannot produce Atlantic's forcing to the Pacific. It actually generates, this is the warming along the equator. It produces a greater warming. But once the Atlantic forcing could be on the Pacific could be simulated in this second group, this warming in the Pacific is much less. But this warming is El Nino-like. So it actually would put, and the global warming, the Atlantic is actually warming quite fast. So that warming in turn would cause a cooling in the Pacific. But if that is not there, you produce too strong a warming. And that would have implication for the South America's future climate projections. Because South America mean state change is actually, in the future, is El Nino-like. So if this is weaker with realistic modeling, then that change will be weaker. The other one is, I tell you about this alpha, right? This alpha. This alpha, this is a skewness sum, right? This skewness sum. If I select this group of model, and I call it bad model, and I show the future change in rainfall in March, April, May in South America, compared to this group of model, which is more realistic, they are very different projections. So whether a model is able to simulate this nonlinearity is quite important. So in this group of model that could simulate the nonlinearities, actually the rainfall in this part is projected to increase. But in this bad model, it's a different story. You can still see the dipole structure. So whether a model is able to, I suspect this would have a lot of impact on the monsoon, in the future monsoon, right? And again, so this alpha is a measure of diversity, whether a model is able to produce diversity. And again, if you look at this group and looking at the teleconnection change in the future. So this is good models in the present day climate, teleconnection rainfall, which is reasonable, right? You got the dipole, you got the, during El Nino, this is E index, not C, E index, teleconnection to E index. You got, along the coast, a bit of, and this is the west coast, a bit of increased rainfall in Southeast America, and in the future intensify, right? Where there is significance from future to present day is steepled here. So this is the in a good model, the changes in the teleconnections. Now you look at the other group of model, it's quite different because now you can see this teleconnection is quite different. The drying is closer towards the west coast. And look at here, the future change is much stronger in the north, in this region, much drier when El Nino comes. Now this, how do we know which one is right? We don't know. But if you have to bet, you want to bet in a good model, right? The probability of this is right is higher than this. I think so. I think that's the way to put it. So in terms of how this might impact on South American monsoon, I hope that we could explore in the upcoming years together. And so I'm going to finish my talk. I hope I don't use too much of my time. So yeah, so under global warming, although models simulate very different ENSO pattern from one model to another, if you look at models' own variability at models' own center, there is this emerging consensus that ENSO variability will increase under global warming. And that increase is underpinned by quite a nice dynamics that under global warming, the upper ocean is warming faster. The stratification intensifies, right? And that should really translate into more extreme events. Now, the mean state change, the teleconnection change in terms of their projections, it really depends on the models. So understanding a model's physics is actually very important. And I think that's my message. Thank you very much. This will be in our paper. Yeah. Yeah.
Yes, with bad models and
Yeah.
good models.
Yeah.
And I found
The other one.
even more interesting that one of the
Yeah.
Australotto.
Yeah.
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 This one.
Yeah.
Because it changes considerably what happens in northeast Brazil.
Right.
Which is
Right. Exactly. Yeah. It's very important here.
This is the season.
Yeah. So this will be in our paper. This two figure will be in our paper.
Yeah. No, it's very, very interesting because it changes the projections for Northeast Brazil in the rainy season
Right,
there.
in the March, April.
It's
March,
really...
April, May.
Okay, questions?
Yes.
Very, very interesting talk. I'm wondering, because you showed these two major El Niños of the past century.
Right.
I'm wondering about the 2015-16, how well if it's in this kind of, is this the new El Niño we are talking about? Because teleconnections were a bit different this time.
Yeah. So 2015 and 16, when I published that paper, it wasn't in it, of course. But in terms of rainfall definition, it's still past the extreme El Nino definition, 5 minutes per day in DJF. But actually, the maximum rainfall and the maximum warming is not in the eastern equatorial Pacific. It's actually in the central Pacific. So, and so the impact is quite different. Now, how different from 1997? There are many differences. The SPCZ, the South Pacific Convergence Zone, doesn't shift dramatically towards the equator by 1,000 kilometers. We didn't see the eastward propagation. So in many respects, it's a mixture of Central Pacific and Eastern Pacific El Nino. And there are, of course, many, many papers about it now. So one of the theory is that over the past 20 years, the Atlantic forcing of the Pacific cooling has generated a more cross-equatorial wind, and the cross-equatorial wind is able to generate a cooling on this coast that offset the warming to come from the Central Pacific. Normally, a Kelvin wave would take the warming into this region, but there's because of the cross-equatorial wind that drive a cooling. Yeah. So there are many other theories about it. Yeah.
Thank you.
Hi.
Under global warming,
Right.
One would expect that the convectively coupled waves would be more coupled, in the sense that the waves are probably going to be a little slower, and therefore the coupling with the ocean becomes more efficient. That's probably what explains the coupling. Now the question is, do you know if anybody has explored this difference between the good models and the not so good models?
Very diplomatic.
In terms of the characteristics of the convectively coupled waves. In other words, there's probably some differences in these models, and it would help us understanding why, right?
Right.
You have this kind of different.
Very good question. In fact, no, not many studies have been carried out in that respect, but I think it is actually one of the key. So convection in a model is key. How that convection is able to establish itself. What is the convective threshold value in a particular model, and whether that threshold value is really anyway mimicking what in the observation is actually very important. Now, under global warming, the stratification is intensified. So if you look at the first three modes of volcanic wave modes in the equatorial Pacific, they are all intensifying. Yeah.
Any other?
My main interest is on the impacts of El Nino. And we know that under El Nino, we normally have less hurricanes in the southeast U.S. What is your expectation under global warming with the intensity and number of hurricanes that we may experience over there?
You mean which part of the country? Say it again. Which part of the world?
In the southeast USA.
Southeast USA.
Yeah.
Southeast USA. You're talking about the Atlantic
hurricane season.
Yes. Atlantic hurricanes.
Yes.
So Atlantic hurricane is pretty much influenced by the SST in Atlantic. So during 1998 La Nina, you had the Hurricane Mitchum or some that name, which caused huge damage. So I think it's still true that under climate change, the total number of hurricanes may not change much, but the extreme ones, that is really a killer increase in frequency. Yeah. Mm. Mm. Right. Okay. Again, very good question. So many of the models do not simulate the observed hiatus, right? And that is an indication that maybe climate models, decadal availability, tend to be too weak. Because if it is at the right amplitude, you expect the warming to be offset by the negative phase of the PDO. But how do you actually get the climate change signal out of so many models, given that each model has its own variability? Ensemble, multi-model ensemble is your way, because each model has its own variability. When you have enough number of this random decadal variability from a lot of models, you tend to get rid of the variability-driven signals. So once you aggregate on many models, you are pretty right to assume, may not totally, but pretty right to assume there's offset from one model to another of the decadally generated signals. Did I answer your question? Yeah. Okay. Thanks. Thank you. Yeah. All right. I'm afraid no, I haven't done that yet. So, but I think it's important as well. Yeah, I think this kind of model world, it offers so much that if you can go and have a look, although it has a lot of limitation at the moment, the model, some of them are not very good, and maybe so the resolution is a little low. Yeah, a little low. Yeah. So, but a group of us, including Alice, we are looking at this South America's ENSO's impact on South America, how it will respond to climate change. We're looking at many things. And I'm hoping that will be a good start, and I'm hoping that it will also stimulate a lot of interest in this area. And that's why I'm coming here, really.
Your talk was a very effective way of doing it.
Okay.
As you saw, it aroused a lot of interest.
Okay.
We just have to stop here.
Right. Okay. Thank you very much. Yeah.
Talk,
Yeah.
very, very interesting, this objective way of assessing the performance of the model related to this Eastern and Central El Niño. Very good. These results are very interesting.
Okay. Thank you.
Okay,
Thank
very
you.
much.
And I look forward to learn from you in the next 2 days. Yeah, I'm looking forward to learning from all of you. Okay.
Thank you. So,
This one.
okay. Now, Manoel, then, we present a talk which is very important introduction to the American monsoons. He will describe the main features and life cycle of the South American monsoon.
Esse ó, porque de longe, de perto. Previsão display, full screen.
Good morning. Well, I will talk about the main features and the lifetime of South American monsoon system. Good morning. Well, I will talk now about the main feature and life cycle of South American monsoon system. As you know, the monsoon word refers to seasonal rains associated with the change of the wind direction. The monsoon seasonal change is characterized by a variability of the physical mechanism, which produces strong winds and wet summer and dry winter. There are three factors mechanisms which drive the monsoon. The first one is the differential heat between land and ocean. This is a figure for South America. Then here is the continent, Pacific Ocean and Atlantic Ocean is high. The color, divergence and the convergence, and the vertical circulation. Then when you have the thermal gradient from continent to ocean, the pressure fall here in the continent, and you have the circulation from ocean to continent, then create a convergence, mass convergence here, and you have an intense ascending movement. Then you create west-east circulation. Now this circulation is a characteristic of monsoon system. Another mechanism, is the Coriolis force that is important when the westerly cross the equator in the Pacific, in the Indian Ocean, when again, South America, when the easterly cross the equator from north hemisphere to south hemisphere, they deflect into right, then penetrating the continent. The other mechanism, the ability of the water to evaporate and condense in the atmosphere. This is important to transport moisture from ocean to continent. Well, as Alice talked, say before, this definition of the remedy for monsoon is characterized as well, this has three important things. That is the wind did change between the winter and summer. This change in the wind that need shift at least 120%. The frequency needed to maintain this wind. Do not necessarily change very much. That is maintain at least 40%. And need a limit of the velocity. It exceeds 3 meters per second. And as Alice showed, this is region that is dominated by monsoon system according to the Ramage definition. South America is not complete with this definition. Why? Well, the wind doesn't change in the summer to winter. You see anticyclonic circulation in both seasons. Why the wind doesn't change? What happens in other continents? Well, one explication of Ramage is the continent in sublatitudes and the extratropical latitudes is very narrow. Another thing is because the resurgence you have here, and the resurgence maintain the water cold water all months of the years. Then because two reasons, you don't form a anticyclonic circulation here in the continent. Then display why you don't change the window in the winter to summer. Well, but if you see the annual cycle of the precipitation, you see that you have a winter dry and in summer wet. This is the annual cycle for each point of this grid. In January is the left side, in December is the left side. Then you see that you can be a monsoon system according to the annual cycle of the precipitation. Zoe law shows that if you remove the annual mean of the winds, you can see the change of the wind. In the summer, you have northwest to southeast winds, and in the winter, the opposite. But it's true to say if you remove the annual cycle, you see this contrast, the change of the wind, you can characterize as the monsoon region. But if you look only the zonal wind, not the total wind, because the meridional wind, all months, it is always from north. Is more intense in the winter, less intense in the summer. But the zonal wind change its direction. If you see the high and month, yellow here and red is easterly, and blue westerly. Then you see that in the dry season, you have easterly. This is for West Central Brazil. But when the rain season starts, the wind changes direction to westerly. This is important because this change the direction of the zonal wind, when it is from west, they transport moisture from Amazon to central Brazil, southeast Brazil. In upper level, you can see that you have change, but the opposite that in low level. Then the shear is inverse in the summer that then in winter, the vertical shear of the wind. This is also for zonal wind in low level, that the color is the same as the other. The white here represents the Andes Cordillera. Then you see that here is longitude time. It's the mean in this latitude belt. You see that in the dry season or winter, you have easterly. Then in September, they change to westerly, just close to the Andes mountain, Cordillera. And this is propagate to east, reaching in around 50 west in end of November, beginning December. If you change the projection, you put latitude here in this belt, you see that the westerly propagates to north in September, and you create one region here with westerly, and here easterly. Then you see that you have a cyclonic circulation that is associated with the chacolau. It's a characteristic of the summer circulation here in South America. In upper level, you have the center, the circulation. In the summer, you have the anticyclonic circulation here over Bolivia, then known as Bolivian High. In the northeast Brazil and Atlantic, you see this trough. This is anticyclonic is a characteristic of a monsoon system, and this circulation is a characteristic of the summer circulation of South America. In the winter, you see that the westerly, but Alice is present here that you have other definitions to monsoon, and she present associated with precipitation. But Asnani in 1993, he suggests that you can define monsoon using the position of ITCZ. Then he defined that monsoon, the monsoon regions lies between the 5 north of northmost position of the ITCZ and the 5 south of the southmost position of the ITCZ. This disappeared. Acabou. Deixa eu ver se... O mouse não... Cadê a luzinha? Thank you. Then this line represents the climatological position of the ITCZ in July, and this in January. Then, if you put 5 degrees north and 5 degrees south, you see that in this region of South America, in the tropical region of South America, it's possible to say that you have a monsoon regime according to the Asnani definition. Well, here is a composite of the onset data on Central East Brazil. This normally happens in mid-October. Then, in 9 pentas before, just 45 days is beginning September. The convection starts here, and the convection here is connected with the ITCZ, Pacific ITCZ. And the convection propagated to southeast, quickly as a characteristic of the monsoon, and form a band northwest-southeast, sometimes associated with the South Atlantic Convergence Zone. Then in November, start the onset. The onset is in southeast Brazil. This is a line of the onset. This was the Silva Diana Kosk. And you see that the onset, the rainy season is starting in northwest South America and propagates to southeast, as you see in the composite. This is for the end of the rainy season, then starting in São Paulo State, basically, and propagates to northwest, reaching here in May. Interesting to see that this propagation of the dates coincide with the change in the windows, in the zonal window. Then you can say that the start the rain season when they change the easterly to westerly in zonal winds. Well, in this study of Grimm et al. 2004, they identified the dates of onset and demise. For this region, the Central West Brazil, they found that the onset is between middle September to middle November. Just in this period, you can see the onset rain season. In average, is in mid-October, with standard deviation 3 pentas. The end of the rainy season is between April, beginning of April and beginning May. In average, middle of April, with the standard deviation 2 pentas. You see that you have more variability on that set than in the demise data, because the onset is more associated with the transient system. Because normally in the onset, you have on transient. In South America, you have the paper of the Fu that shows in southeast of the Amazon region is associated, the onset is associated with the cold front. In central of Brazil, most of the years is also associated with cold front. But I saw 2 or 3 years that a cutoff law that formed in South Pacific Ocean when propagated to east, cross the ends, and they can organize the convection and start the onset. But in the most of the years, the onset is associated with a cold front. All the characteristic of the monsoon is you see the annual cycle of the temperature in low level. You see this time and latitude, that you see that the maximum you have in September, just before the onset in Central East Brazil, that is in mid-October. These figures you can see better. Here is precipitation. This line is the temperature in low level for this period in this region. And you see that the maximum temperature is before the onset, that is in mid of October. Sensible heat flux have a pattern similar to temperature, but the maximum is in October. The specific humidity has a minimum in October, September, and the maximum in December. In the latent heat flux, have a similar pattern of specific humidity. But this is important because this surface heat flux has some importance to destabilize the atmosphere. I will show 2 years, the same figures, but for 2 years. 1 year, that is 2003, that is the onset was later than climatological data. And here you separate in 2 figures, but you have some information in both figures. In blue is the sensible heat flux. In red, the latent heat flux. But in this figure, you have the temperature, in low-level temperature. In this figure, you have the specific humidity. Then you have here the behavior of the sensible heat flux, similar to the temperature, which is the maximum before the onset, that's late. But interesting here is the latent heat flux that the increase very has an abrupt increase in the September, but the latent heat flux does have the same pattern. Maybe this is because you have more moisture coming from Amazon region, but it's not converting in precipitation. Then the latent heat flux doesn't increase like the specific humidity. Now, when you compare with this, that early onset, you see that the specific humidity have the same pattern that the latent heat flux. But the temperature here is low than in the other year. Here, the temperature is higher than when it's early. Well, you can imagine that the onset is later, you have more solar radiation. But when I saw these figures, I remember the study of Grimm et al. 2007, that she shows that if you have a spring with dry conditions, you, in the case in Central Brazil, Central East Brazil, then the temperature in surface is high because you receive more solar radiation. The soil moisture, you have less soil moisture in the soil. They observe also that the positive anomaly of sea surface temperature. With this condition, the pressure fall more than normal. Then you create in the summer one anomaly of cyclonic circulation. When this anomaly is more, the cyclonic is more intense here, you have more transport from Amazon to southeast Brazil. Then you have more precipitation in the summer. Well, this is a study of my student that identified the onset for Central East Brazil using the same criteria of the ENSO, the change the zonal wind in low level. And they identify that this pentadas is the more years, the onset is here. In Ghana et al. 2004 found in this pentada. But here you have the maximum in the middle October, basically. And he did the composite with the mean in the early and later onset. But he studied some difference when this happened. This is interesting. You see that this is a composite. The pentada 0 is the onset. The blue line is when the onset is early. It is a middle, the green. In red is later. Then you see that the early, before the onset, you have less precipitation. But during the rain season, you have a little bit less precipitation. But when you have late onset, you have more precipitation early the onset and before the onset and the late onset. This is composite with the precipitation and the wind for the total, the 30 years. Then it's similar that you outgoing long-wave radiation that propagates starting in the northeast, northwest South America and propagate to southeast. Here appear another center. This is interesting. Is associated with the low-level jet. The low-level jet, before the onset, they go direct to South Brazil and create this maximum of precipitation. When the onset is approaching, you see that the wind change direction. We have the zonal wind increase. And you have here more convergence of mass convergence here. And then contribute to you having more precipitation. This is for early onset. You see you having less precipitation. This center continuing appear. But suddenly starts the convection in the Central West Brazil. When the onset is late, it's interesting because the convection is you observe north of the region. That here you have the rainy season, but it is concentrated this part, not here. But suddenly propagated to south, as you see here. Well, when this is for upper level, you see the Bolivian high, anticyclonic circulation that is now over Bolivia in this position and propagated to south in the pentatone plus 4. When you early, you see basically the same configuration, not changing very much. You compare, you see, only the intensification is different. But when you compare with the late onset, you see that the anticyclonic is displaced to west. It is more intense than the other two cases. Oi? In this is a position is different. Here is most close. You have more precipitation. You have more strong. Yes.
This mechanism you described before. when you have less soil moisture.
Less soil moisture, more temperature.
Yes, and then you have a dry onset, so you don't have an early onset, and then the soil moisture decreases, temperature increases, and then this local cyclonic anomaly circulation forms, and then you have the late more precipitation in central east part.
Yes. Is agree very well with the. I will show now the picture that you see. Here is the cross section, latitude for high, and here is longitude. For 2 pentas before and 2 pentas later onset in the middle. Then you see here that this the region you are interested in, Centro-West Brazil. Then you see that 2 pentas before you have dissident movement in upper and middle level and ascendant in low level. This, the ascendant low level can't go to up troposphere because it's blocking by this descendant movement. I forgot to say you that this line is equivalent potential temperature, that you see a gradient associated with cold front. Then part of the movement ascendant goes to in direction of the cold front, and the other part goes to north hemisphere. But when the onset starts, this circulation, the ascendant circulation, go to the troposphere, then forming the northeast circulation very well. And this west-east section, you see the same. You have the descendant movement here, the ascendant, but the onset, the ascendant goes to the tropopause and forming the west-east circulation, associated with the monsoon system. This is for early. Is a pattern similar, but you have more intense subsidence movement here, but this change is not so intense, it's a little bit weak. The same here, you see. But when you go to the late onset, interesting here, because in 2 pentas before, you see the south to north circulation north of the region. As you see the convection, this represents very well. But in the onset, it displaces to south, and the ascendant branch is over the Central-West Brazil. Then continue in more intense circulation. Similar happen here, east to east, and you have the intense circulation here. The big C breeze. This is another study. In the left side is a temperature anomaly. In the right side is the specific humidity anomaly. This is interesting. This started 12 pentas before the onset. Here's the onset. Here 12 late. Then you see that before the onset, the anomaly, a positive anomaly in the continent, a negative anomaly in the ocean, is remove the zonal mean. That the anomaly is around, the positive anomaly is around 700 millibar. But when the onset starts, this anomaly positive appear to tropopause. That is associated with the latent release, latent heat release. That is more intense. The humidity, specific humidity, interesting because you see a dry center here in Central-West Brazil, but this center disappear after the onset date. Summarizing this vertical cross section, this is figures show very well that you have here the convection associated with the winds coming from the Atlantic Ocean. And here you have convergence associated with a part of the low-level jet that goes to Central West Brazil. And you have convergence and movimento ascendente, and you have the breeze, the east-west circulation. Other movement ascendente you have here associated with the Andes mountain. You have a subsidence under the Pacific Ocean. This is another view of the characteristic of the monsoon system of South America. This is the zone law. In number one, shows the flow coming from the North Atlantic that penetrate in the continent. They turn to southeast. Here, form, in some cases, form a low-level jet. And when reaching this North Argentina, South Brazil, form a cyclonic circulation associated with the Chacolau. In 4 here shows the anticyclonic circulation with the South Atlantic. In the South Atlantic, that you have a branch penetrating the continent, and you create a convergence zone here. And this is known as a South Atlantic convergence zone, or ZACAS. In 6, you see the westerly. In 7 is the in upper level now, the anticyclonic circulation, Bolivian high, and part of this branch goes to North Hemisphere. And the zone law, they identify 5 phases of the South America summer monsoon. The first phase is associated with pre-monsoon. It starts in 1st October and goes to 19 November. The second phase is the monsoon development, is during this period. The third is the monsoon mature, in this period, that is January, part of February. Withdrawal, the end of rainy season, start in February, like you see the other figure, and go to 9th March. And post-monsoon is the period. Now you show some characteristics with each phase in low and upper level. This is the... Then in upper level, in phase 1, you see that you have divergence here, diffluence and divergence. Here you see the easterly penetrating the continent and form a convergence region. That this convergence in low level, the divergence in upper level, means that you have convection here, as you saw in other picture. In upper level, you find here the strong wind, the jet, in the subtropical latitudes. In phase 2, the anticyclonic is more defined now. You have a trough of the South Atlantic. The jet propagates to south. Now is a polar jet. In low level, the easterly penetrates the continent and returns to southeast and forms the Chacolau. And there you have the confluence here. Confluence here and divergence here, you can take more precipitation in this region. Now here is the difference of precipitation between these 2 phases. Then you see you have less precipitation here in this region and more precipitation in this region. The third phase is the mature. You see that the Bolivian high now is over Bolivia. In the northeast Brazil, the trough close form the cutoff law of northeast Brazil. Studied for many people, Maria. And in low level, the shackle law disappear, but you have the convergence flow here in this region. The strong wind is more to east. This different precipitation of these two phases. You have less precipitation here and more precipitation in this part of South America. For withdrawal phase, you see that the cutoff law now is open. You have just a trough. The anticyclonic circulation is not so intense and propagates to north. In low level, you could see the branch that the flow coming from northwest South America to southeast South America. You don't see more this flow. That the easterly goes to the Andes Mountain. In upper level, you see also another one differential here in the flow, the westerly. This difference of precipitation, you have a maximum precipitation here, no positive values here, and negative here, less precipitation. In the last phase, the upper level, the anticyclonic circulation is very weak. There is a little center, but you have a ridge here, and the trough here is weak also. In the low level, the easterly reaching the Andes, a part goes to south. And the strong wind, westerly, propagates to north. This is different precipitation. Now you see that you have negative values in basically a large part of South America, a positive all in northwest of South America. This is a composite to the mais period in Centro-West Brazil. Then you see the precipitation in the summer, in the February. Then is the precipitation returning to northwest South America. Well, here you can summarize basically the talk. That you have the ITCZ, Pacific ITCZ, that connects the convection all in September when the convection is more in this region. The Atlantic ITCZ is connected with the convection during the summer. Is important system here is exact South Atlantic Convergence Zone. The shackle law, you said, the low-level jet. If it go more to south, you have more precipitation here. But when it changes its direction and you go to central, west central Brazil and southeast Brazil, you see more precipitation in this region. In upper level, you see the anticyclonic circulation with the trough in northeast Brazil. That's it. Thank you.
Have you seen a connection, because you showed the kind of hadron circulation, and now you showed the South American monsoon and ITCZ. Have you seen a connection between ITCZ and the South Atlantic Convergence Zone, maybe in terms of intensity, or when one is more intense, the other is also, or vice versa?
Sometimes it happens here when you have a South Atlantic Convergence Zone intense, or when one cold front penetrates to low latitudes, the pressure fall in this region, and ITCZ normally displaces to south. And you have a connection between the clouds, like you see here, the ITCZ with the convection on the continent and South Atlantic Convergence Zone. But more intense or less intense, if you have more connection, I didn't study this. Yes.
This is maybe a naive question. So in this picture, right? So you have the ITCZ, the SACZ, and so during El Nino, for example, right, the ITCZ would not come through because I think you may cause a tropical North Atlantic warming, so the ITCZ may not come through. Now, in that case, what would then happen to SCZ when an ITCZ cannot come through? Huh?
South Atlantic Convergence Zone.
Right, the SACZ, South Atlantic Convergence Zone.
Yeah, well, did you get the question?
Yeah.
So
Right.
if the ITCZ goes northward, okay, which actually happens during El Nino, for instance, in fall. What happens with the SACZ?
In the in the beginning, the convection in northwest Brazil. You studied the correlation with the precipitation in southwest Brazil and the southeast, central west Brazil and southeast Brazil with the sea surface temperature in the Pacific. And it does show a correlation with the onset and the sea surface temperature of the Pacific. But when you have strong extreme precipitation here, summer with extreme precipitation, you see a correlation with the ITCZ in Central Pacific, not in the Eastern Pacific, but just in the extreme precipitation in Central West Brazil, you saw. Yeah, no, not correlation. Correlation that's true, but but when you make a composite with more precipitation in Central West Brazil, and you compare with the sea surface temperature, you see a Modoc El Nino. Or the Central Pacific anomaly is higher.
No?
I would like to just make a comment. The late onset of the SAMs and early onset of the SAMs, you took the years in two different phases of the PDO. One of them is in the cold phase, another one is the warm phase. So I guess this difference may also be related with the PDO phases.
Interesting. These are interesting points to study.
Yeah, actually, may I make a comment?
No.
Well, I think it's related to what happens at the beginning of the monsoon season there in Central East South America, when the large-scale influences make climate drier there, then happened this chain of this sequence of, let me say, actions. He described it before. So it gets drier, less soil moisture, higher temperature, and this topography, yeah, please, go back. This This topography in Central East Brazil helps this process of enhancing convergence there. And then you get this regional cyclonic circulation, which then in the peak monsoon season diverts this moisture flux into Central East Brazil. He showed it in his composites of late and early monsoon onset, exactly this. So when you have early, so can you see there? When you have early monsoon onset, you don't have much precipitation in Central East Brazil, okay? Just in this northwest, southeast band. Yeah? But then, when you go to late, see how it extends to Central East Brazil because of this effect. So this relationship between spring and peak summer precipitation in this region. Yeah. Of course, this relationship is modulated by interdecadal because this interdecadal influence, it contributes to dryness or wetness in Central East Brazil in spring. In spring, yes, it's modulating this effect. Yes. Mm-hmm. Okay, well, thank you very much, Manoel.
Thank you.
Okay, now we have the coffee break, and after the coffee break, you stay around outside this door. We'll have a group photo, okay? Ela queria falar comigo, podia ser agora no café.
Porque está meio atrasado, né?
Sim, sim. Yeah. Please be back at 11:30.